Hello and welcome to this screencast on exponents. So what I'm going to do here is I'm going to draw a variable. So I've got a variable a, and what I'm also going to do is after the a, just to the right, I'm going to put a superscript, n. Okay. Now this is an exponent. So what we say is the n is the exponent, okay, of a. Also, can be also known as a power, which is fairly common, or indice or index. Okay, so n is the exponent, a is the base. Okay, and what does this mean? Well, a to the power n is simply a multiplied by itself n times. Okay, so I don't know what n is, n could be a large number, but a multiplied by itself n times is the same as saying a to the power n. Simple example, 2 raised to the power 3, simply 2 multiplied by 2 and multiplied by 2. So 3 lots of 2 multiplied by each other. And if we do the sort of powers or exponent or indices, whatever you know them as. Okay, what I'm going to do is I'm going to talk about there are 3 laws of indices which can help us. Okay, so first law, okay, is to do with multiplying indices. So if I have an index, a base a raised to the power m, and I'm multiplying it by the same base a but raised to a different power, I can simplify that by saying that's the base a raised to the power m plus n. Okay, so notice the base has to be the same quantity. The powers don't have to be the same quantity, but if you've got a base exponent multiplied by another exponent with the same base, the powers. Okay, that's the first law. The second law is where we divide. Okay, a to the power m, divide a to the power n, for example, and in this case we subtract the powers. Okay, so when you multiply, you add. When you divide, you subtract. And the third one is where we have a power of a power. So I've got a quantity a raised to the power m, and then whatever that is, raised to the power raised to the power n. Okay, in this case, we multiply the powers together. Okay, and these laws are known as the laws of indices or laws of exponents. Okay, and let's have a look at some examples. So, what if I had 2 to the power 2 multiplied by 2 to the power 3? But if I expand these out individually, 2 to the power 2 is 2 times 2, 2 to the power 3 is 2 times 2 times 2. So what we have here is I've got 5 lots of 2s multiplied by each other. Okay, so that's 2 to the power 5, and you can see that is actually 2 to the power 2 plus 3. So you can see it all makes sense. All of these validates the first law. What if I have 2 to the power 3 divided by 2 to the power 2? Well, on the top, I've got 2 times 2 times 2, and on the bottom, I've got 2 times 2. Okay. If you know your fractions, what we can do is we can cancel out a 2 on the top and a 2 on the bottom, and we can also do the same for the other one, and we get 2, and that's actually 2 to the power 1 because it's just 2 on its own. Okay. You can see 2 to the power 1 is the same as 2 to the power 3 minus 2. So again, this validates the second law. Okay, and finally, well, we have 2 squared to the power 3. So what I have here is I'll have 2 times 2 multiplied by 2 times 2 and multiplied by 2 times 2. So 2 times 2 is the 2 to the power 2, those multiplied by each other. So if we ignore the brackets, you can see there are 6 lots of 2's, so that's 2 to the power 6, which is actually 2 to the power 2 times 3. So all of these 3 validate laws of indices, or laws of exponents, sorry. Okay, well, exponents, to prove a couple of quite nifty results. Okay, so the first result I'm going to look at is what happens when we raise a number or a quantity to the power 0. And I'm going to spoil it for you straight away. I'm going to say that any number, any quantity raised to the power 0 is equal to 1. Okay, so let's have a look at a proof of that. Okay, so what I'm going to do to prove this is I'm going to say, okay, 1 is equal to any quantity divided by itself. Okay, and the quantities I've chosen to use are a to the power m. Okay, well if I use the second law, I have a to the power m minus m. Okay, and m minus m is 0, so a to the 0 is equal to 1. Okay, so for example, if we had 10 to the power 0, that's equal 1. If we had 99 to the power 0 equals 1. If we had a ridiculous number I'm going to make up to the power 0, that's meant to be a 0, that also equals 1. So any number to the power 0 is equal to 1. That's the first result. Okay, that's a result you're going to have to remember. And the next result I'm going to look at is what happens when we have a negative power. Okay, so a to the power minus n is simply 1 over a to the power n. Okay, so this is another result, one of these results you're going to have to remember. Okay, and if we have a look at a proof of that, so 1 over a to the n, well, instead of the 1 on the top, I'm going to actually write a to the power 0, because on the previous result, I showed you that a to the power 0 is equal to 1. So I've not changed the value at all. Okay, and if we use the second law of exponents, we subtract the powers. So I have a to the power 0 minus n. And 0 minus n is simply minus n. Okay, so that's a proof that whenever we have a negative power, we could write that as 1 over the positive power. So examples of these, so 2 to the power minus 1 is simply 1 over 2 to the power 1, which is actually a half. Okay, what about 2 to the power minus 4? That's simply 1 over 2 to the power 4, and 2 to the power 4 is 16. Okay, so whenever you have a negative power, you can write that as 1 over the base raised to the positive power. Right, the last thing I'm going to look at is what happens when we have fractional indices, or fractional exponents. Okay, and to start with, I'm going to show you what happens when we have a raised to the power half. And what happens here is a raised to the power half is another way of writing the square root of a. Okay, and just to remind you, a square root of a number is simply another number. If square root of a equals b, that means that b times b is equal to a. Okay, so for example, square root of 4 is equal to 2. So that implies that 2 times 2 is equal to 4. And you can see that is indeed correct. Okay, so what happens if I've got a to the power half? What I'm going to do is multiply 2 lots of a to the power half. Okay, but by the first law, so because we've got multiplication, we simply add the indices. We've got a to the power half plus a half, and a half plus a half is a to the power 1. So that implies that a to the power 1 half is equal to the square root of a. So what does this mean? If we have, for example, 16 to the power half, that's the same as saying the square root of 16, which is 4. Okay, you can extend that. What about a to the power a third multiplied by a to the power a third multiplied by a to the power a third? Okay, well, if we use the first law of exponents, that's a to the power a third plus a third plus a third. And again, that's equal to a to the power 1. And that implies that a to the power third is what we call the cubed root of a. Okay, so the cube root of a is written by the square root sign with the 3 just up here. So for example, 27 to the power a third is equal to the cubed root of 27, which is of course 3. Okay, and we can extend this fractional powers, we can extend what we're talking about here to the fractional power to the nth. Okay, so a to the power 1 over n multiplied by a to the power 1 over n. If we keep doing that n times, okay, so we've got n lots of fractional powers of n. Okay, well, if we apply the first law of exponents, we've got n lots of 1 over n added together up here. So that's n times there. Okay, and again, this is a to the power 1, so this implies that a to the power 1 over n is simply the nth root of a.